Good afternoon, everyone. Let me just get this sorted. Right. I hope all of you can see my screen. So, good afternoon, everyone. Welcome to this third webinar of the Zach World of Facades webinar series. Today's topic is on advances in structural glass engineering. Again, very different from the other two topics which we have had earlier in the last few weeks. So, thank you so much for your time. I hope all of you are staying safe during these challenging times. Right. So just to give you a quick overview of till we have some people joining in, we started this webinar series, I think 4 weeks back when the lockdown had started. We got some inquiries from a couple of our friends saying that why don't you do this because we are all at home. This could be a good opportunity for people to contribute presentations and help one another during this time of lockdown. And then we started this. We started this initially as the stay-at-home edition because most of the world was under lockdown, and the directive was to stay at home. So we started it as the stay-at-home edition. We will later on change it to the stay safe edition. Of course, the frequency of the webinars will reduce as we return back to our normal lives. So we'll be doing a few more webinars till we can start the physical conferences back. We hope to have a few conferences by the end of the year when it is deemed to be safe. So till that time, we'll probably do 1 or 2 webinars a month. And we'll probably call it the Stay Safe edition. Today's webinar, like the previous 2 webinars, also has been powered by Schuko. Schuko are a German company manufacturing door, window, and facade systems. They've been supporting us globally and have been a strong supporter of ours in the Southeast Asian region. So this is today's schedule. So I will start with the introduction. My name is Ahad Ahmed. I'm part of the organizing committee of the Zach World of Facades conferences. We'll have a presentation by Ian Langham first, followed by a presentation by Andreas Gehr, and then we have a joint Q&A for both the speakers. So the question and answers will be taken right at the end. You have a questions pane in the GoToWebinar panel. Please post your questions over there, and then at the end, after both the presenters finish, I will pick the questions and I will shoot it at our presenters. Okay, so our first presenter for today is Ian Langham. He's a director at Eckersley O'Callaghan. Eckersley O'Callaghan are structural glass engineers. They are known for engineering some of the large-scale glass at the Apple stores. I'm sure one of us would have at least visited an Apple store to see how beautifully they design the flagship stores. I mean to say, would have designed their stores. They're beautiful. They play a lot with glass, and Eckersley O'Callaghan, or EOC as short as we call them, have contributed to engineering these glass structures, apart from a host of other projects also. So Ian will cover about the future of glass, a retrospective, what did now look then, technology of the present, and our vision for the future. So he has over 12 years of experience and a very knowledgeable person in the field of structural glass engineering. Following him, we will have a presentation by Andreas Gehr. He's the managing director for Sealay in Southeast Asia. So he's going to be talking about Sealay is a specialty contractor doing special stuff, complex stuff, and he will be talking about the projects they are doing in Southeast Asia. He has a couple of very interesting projects to show which they have executed in Bangkok. So he will be talking about the challenges he has faced with respect to the local building law codes, supply chain, logistical challenges, and the installation challenges. So what he's going to talk about is large-scale glass, and again, transporting them, installing them is a challenge anywhere in the world, but in Asia, it's an even bigger challenge. So he's going to be talking about that. So of course, he's had 2 stints with Sealay. His first stint was in '97 with them. Then he was the technical director and managing director for Schuko in Southeast Asia. And then he rejoined Sealay back in 2017. So he's based out of Singapore, and Ian is based out of London. Before we start, our next webinar is again on a different topic. This is on fire safety in facades. It's brought to us by our friends from SideRise. So we have Mr. Masood Moinfar from Ferestra Malaysia, who's a facade consultant based in Malaysia, talking about what not to do on facades. And then we have Mustafa from Warrington Fire, who are a testing laboratory, talking about which is the right test for the full-scale system tests. I won't take much of time. I will go straight ahead into the topic and give Ian the control. So Ian will now be making the presentation. So over to you, Ian.
Okay, thank you. And just bear with me a second. Okay, I'm going to turn off my video just to help with the bandwidth. Okay. Okay. Hopefully you can see my screen.
Yeah, we can. Andreas, if you can just switch off your camera, So I've muted you. If you can just switch off your camera, then it will be good. Yes, Ian, go ahead.
Okay. Yeah, afternoon or morning, depending on where you're joining on from around the world. My name's Ian Langham, and I'm a director at EOC. I'm based in London. I lead one of our specialist teams that focuses on glass and complex envelope and structural engineering. So it's a pleasure to be here and asked by Zach to share some thoughts and insights with you today, particularly given that it's quite difficult at the moment to meet people in person. I know the overarching theme of today's webinars is structural glass, but I will stray onto other aspects, and I feel these are equally as important. And hopefully you'll still find it interesting. I know there'll be questions at the end, but please feel free to email me. My email is shown here if you've got any specific queries or want to discuss these topics further after the webinar. So, given the type of specialist work EOC does, we often get asked the question.
Sorry to interrupt you. The screen which I see is just the future of glass retrospective. It's not gone yet into full screen mode. I can see your whole PowerPoint window.
Okay, it's in full screen mode my side. So let me.
I think it's stuck here.
It says pause.
Can you just check? Just check. Can you click the play button if it's not paused or something like that? Can you just check that?
I will do. I will press play. Is that any better?
Nope. Not
let me
yet.
try. I will come out of it and I will come back into it again.
Right.
Okay. Sorry about it.
Yeah, I can see it moving now. Can you just put the full screen now and?
Okay. Can you see that?
Just a second. No, we saw you clicking the presentation mode, but it's getting stuck. Right. Ian, what I said. Hold on. Okay, it's full screen now. It's working now. Can you just go to the next slide? Yeah, it's working fine. It's working fine now. Go ahead. Yes.
Okay, you can see that? Okay, I'll carry on.
Yes, perfect.
Yeah, so I was saying, given the type of specialist work EOC does, we often get asked the question, what's the next big thing, or what will glass technology look like in perhaps 10 years' time? And I think this says a lot about people's desire to have the latest technologies and materials, and normally before their rivals, and how we dream and imagine of solutions that don't yet exist, just out of reach, or more often than not, way out of reach. Whilst we can use the metaphorical EOC crystal ball to get a good idea of what's on the horizon through our close links with industry and monitoring trends, our answer to these questions will always have its limits. But this got me thinking about what were the questions and imaginings that were asked and thought about 50 years ago? How close or how far have we come from realizing those today? So today I will look back to what we envisaged glass technology would be, and look at some more recent developments and consider possible new areas for innovation in the future. The 1960s are pretty synonymous with sci-fi futuristic images and they were freed from technical constraints, and people's imaginations often ran riot to project visions of their wants and desires. This was during a time inspired by the rapid and audacious achievements of the space age, so it was only natural to speculate about what was coming next. And recently I stumbled across a series of 1960s advertisement illustrations from Motorola. The theme was House of the Future, with transparent structures and glass enclosures featuring very prominently in most of them. And this is typical of many sci-fi futuristic musings of the era. But this led me to wonder, how far-fetched are some of these ideas, and how close have we come to them now? It's perhaps no coincidence that around this same time, the possibilities for glass on buildings advanced significantly through the revolutionary float glass process that had been developed by Pilkington. This meant that large volumes of high-quality glass could be produced for the baby boomer generation. And this innovation must have stimulated great inspiration for what the future may hold for glass technologies. But I would ask the question, has there been a revolution on the same scale since? A common theme in the illustrations is this one shown here, which seems to be some sort of luxury residential building, shows large format glass panels. These ones here appear to be around perhaps 6 meters tall, 3 meters wide. And with today's fabrication capabilities in large format glazing, the vision of the future is actually a reality. And in fact, it could have been a lot more ambitious. Some manufacturers can now fabricate panels up to 20 meters tall. Some examples I'm showing here, this one from an Apple store in Boston, where we had to, at the time, utilize spliced laminated glass owing to the size limitations. And other examples, this one here in Hong Kong, this is 16 meters tall, as is this one in Singapore on Orchard Road. These were all made possible by significant leaps forwards in the manufacturing process, led by manufacturers such as Sealy, by investing in autoclaves that could laminate the glass into one piece. In addition, thanks to current interlayer technologies such as Sentry glass, it's actually possible for the mullions and fins that were shown on the 1960s apartment to be completely removed. You can actually have the glass spanning from the floor to the ceiling without any additional supports. And there's an example shown here for an Apple store in Milan that utilizes this process. Although not always made from large format glazing pieces, cable facade systems also enable large surface areas with quite minimal structure and maximum transparency. This is a project we worked on at Wisdom Hall in Bangkok that I'm sure Andreas will talk about a little bit later on today. And a key to successful delivery of these cable type systems is focusing in on the glass to the cable details. And this is something we spend at EOC a long time agonizing and analyzing and refining. More recently, we've been advancing this concept further by fully integrating the cables within the glass system, so they're hidden and they also utilize large format glass, creating facades that are achieving maximum transparency, as shown in this example from a Swire project at Taikoo Place in Hong Kong. This is something we're currently working on. It's around 15 meters tall, but you can see here, it's really achieving this maximum transparency, minimal structure aesthetic. But where will the glass size stop? Transport and logistics are big limiting factors, but perhaps it's no good getting longer and longer panels if we're still stuck at 4 meters width. This example shown in this apartment overlooking the city below shows some single curve glass, perhaps around 4 meters tall. And again, this is achievable today with 18 meter long curved panels actually possible, subject to certain radius limitations, as shown here from an Apple project we did a few years back in Shanghai. But why were they confined to single curvature? Doubly curved panels can be manufactured to high optical quality, either using hot bending over molds, but strengthening is actually limited to chemical toughening, which then has an impact of limiting the size and also possible environmental coatings that are often needed for today's buildings. This project in Brussels combines flat tempered glass with single radius tempered glass and slumped complex curvature glass to create an interesting aesthetic that responds to the surrounding architecture, and again has no fins or mullions. Recently developed cold bending techniques allow flat glass to be pushed into shape and then mechanically restrained in position by either using the interlayer during lamination or via clamping on site. And this has opened up more possibilities in terms of size and geometry for curved glass. An example of this is the recently opened Apple store in Singapore in the Jewel development, and the visual quality is actually improved over other traditional techniques. Today's interest in challenging transparent envelope geometries are inspired in part by advances in curved glass processing, but also in a progression in digital design. And I'll talk about this a bit more later on. As a result, we're seeing a great demand for ever more complex geometry, but this can sometimes be limited by costs, strengthening techniques, and the available coatings. But perhaps we are overdue a revolution in this particular area in curved glass, just as we had in the heyday of the floatline process. And recent developments in double curved tempered glass make this a real possibility, as does further developments in adjustable and programmable molding technology. There are a number of groundbreaking projects currently under development that will show how much of a real possibility this is in the near future. This is quite an interesting image. I think it accurately foresees the idea of using glass as a structural element to create a full glass enclosure or pavilion. The idea of removing visually obtrusive structural elements has long been an objective for designers. And glass has potential for achieving this, but a lack of in-depth understanding of the engineering and a need for robustness has held this back until relatively recently. I'm sure you know we've been lucky enough to work on a number of pavilion projects for Apple over the years, and on each one we've progressed and learned from the previous one. But perhaps one of the most well-known was the project in Fifth Avenue, the Fifth Avenue Cube, which has quite an interesting story because it actually started off life in 2006, comprised of 18 small panels per side. But as production technology progressed, a few years later in 2011, it was redesigned and replaced with a structure that was comprised of only 3 panels, three full height panels per side, and therefore significantly increasing the transparency and removing the fittings, which often are the most visible elements. You can see an example of the difference here. So from these state-of-the-art projects, we learned a lot, and so for the next one, we wanted to be even more ambitious. The Steve Jobs Theatre in Cupertino comprises of a 40-meter diameter carbon fiber roof, supported on curved structural glass panels around the perimeter, and it just goes to show how far you can push the boundaries of glass as a structural material. You know, even the sprinklers and cables that go up to the roof are hidden within the glass joints. And to give you an idea of the scale, we can actually fit all the other Apple pavilions within the internal volume of the theatre. Again, building on the success of this project, it led us to develop other structural glass pavilions, such as those shown here in Istanbul, and this one here in Kunming, which actually includes 5-meter tall pivot doors with titanium laminated fixings, a carbon fiber roof again, and a 6-meter spanning acrylic oculus in the center with no visible joints or supporting structure. And it also had to be designed to withstand relatively high seismic loads as well. You can see that we're continually developing what's possible with glass, contributing as a structural material, and we have some projects that are under development that really push this to its limits and push the boundaries of what's possible. And perhaps next time I do a talk, I'll be in a position to be able to share more information on that with you. I think achieving lightweight staircases that almost seem to float, as shown here, has always been a fascination for designers, even going back to the original cantilever stone staircases from many years ago. a lot of the development work we do around glass is about focusing on the detail and the fixings. And we always try to minimize them as much as possible to make them almost disappear. Some examples are shown here, which show how we could utilize the latest evolution in manufacturing process. But we think that we also played an important role within the project team in making these being developed in the first place. In some ways, these ideas culminated in the staircase developed with Foster and Partners located in Guangzhou, which utilizes the glass facade to double up as the main support and therefore limiting the number of visual elements. And as always, it's a nerve-wracking moment when they do the real life load test, although we have high confidence that it will work. Over the last 10 years, we've realized increasingly transparent structural glass systems by incorporating fittings within the glass buildup. And I think the holy grail for all connections is to be fully transparent, and advances in transparent silicons and adhesives have huge potential, as does welding of glass seams together. And although glass sizes have increased dramatically with large format, they're still limited by transport logistics and local site constraints. And I think more intelligent methods of joining map panels together is another frontier to be explored. For example, 3D printing of glass components is something currently being researched, as is the use of cast glass blocks, such as the example of the Crystal House in Amsterdam, which utilizes UV cure transparent adhesive. We've been also developing our own research projects, such as this glass seesaw shown here, mainly to sort of show how technologies could be best deployed and give some inspiration for others in the industry. Other transparent materials like acrylic could come to prominence owing to their ability for large panels with invisible joints, although their use is currently hampered by fire resistance and limited solar gain performance for facade panels, but this is something that is also currently being developed and progressed. This is an example we're working on, a project in London which is currently under construction, the Skypool. This uses acrylic to span between two buildings around 14 meters, 9 stories high up in the air. This is quite an interesting illustration. It shows their idea of a futuristic glass enclosure that evokes perhaps the greenhouses of old. I'm drawn to the image's depiction of shading. It acknowledges a need for human comfort, but probably not the issue of energy consumption. There may have been less consideration of the solar gain and its associated sustainability impact back in the 1960s. But since then, high-performance coatings and other glass treatments, including solar control and low E, have developed considerably, in part in response to ever-stringent energy requirements and code requirements. The big challenge is always how to overcome the contradiction of having better light transmittance, but also reducing solar gain at the same time. And today's standard technology offers perhaps more reflective and darker glass than was envisaged in this image, but it's making headroads into achieving ever more transparent glass. Looking to tomorrow, current developments in dynamic shading and dynamic glass, which can change the light transmittance and G value, are promising innovations, especially for warmer climates. There are different approaches. For example, the Merck liquid crystal modules are intelligent glass facades that are linked to the building management system, and these could become more common as their costs reduce and people become more familiar and it becomes more established within the industry. Another example is closed cavity facades with integrated blinds, which build on the development of older double skin facades, but integrating the elements into a single sealed unit and therefore reducing the overall thickness. I think the thing that's becoming ever more important, though, is the embodied energy, the embodied carbon, and recyclability of glass and associated components. And it's not just the end performance, and I think this is something that needs full collaboration from across the industry to help deliver truly sustainable buildings of the future. So what would we dream of today? If we were to produce a similar set of images, what would our imaginings of the future be? I wonder how much of today's glass developments would feature in these. Are we overdue another revolution, as mentioned earlier, with curved glass? Or I suspect that we'll continue to see more incremental leaps, branching off into many varied performance aspects and requirements and systems, as shown here, some notable examples over the last 50 years. But there are some areas that we can see might be of particular interest, and I'll just share some quick thoughts on, from my perspective, on how these could possibly develop. So new materials, an area for inspiration could include the high-strength thin glass technologies. These were originally developed in the 1960s for the automotive industry, without great success at the time, but they've been revitalized for the smartphone industry. And they've yet to be really fully utilized within architecture, but they have some interesting potential for kinetic structures to enable adaptability, and also it's useful where weight saving is potentially important. With rising sea levels around the world, will weight considerations become ever more important for things like floating houses as they are for ships today? We've been working in the sector for many years and designed glass for several large super yachts, which require both high strength due to the high wave loads and extreme environments, but also trying to reduce weights wherever possible. We've also been developing our own research projects into thin glass and are currently progressing a scheme that utilizes cold bent thin glass to create an interesting 3D form and glass pavilion. You can see on the screen here, this is our first prototype, which tests the geometry and the fit. But we're hoping to complete the final glass version by the end of this year. There's long been talk of new transparent ceramics, such as so-called transparent aluminium or aluminium oxynitride, revolutionizing the industry. But today it hasn't made significant developments, partially due to costs and complex fabrication. But I suspect in the not too distant future, new transparent materials will become more widespread as evolutions in manufacturing processes continue to happen, and aligning with the digital design developments as well. And just as discovery of things like graphene is infiltrating its way into mainstream use in other industries, I think that there'll be cross-pollination of ideas from other industries back into architecture. But I think sometimes it also takes clients to invest and develop these technologies for them to filter down to wider use within the industry, just as Apple did with large format glazing. Although not a specific technology in itself, the processes and tools that we use to design and fabricate projects which incorporate glass has been advancing significantly recently. And we see digital design as an area that can really speed up progression on many fronts. An example is where we've developed our own scripts to analyze which curved glass types can be used within a complex envelope geometry. And we can make suggestions onto how to optimize the curvature to make best use of the available technologies and hopefully reduce costs for our clients. And it also allows us to optimize the structural design of large span steel and glass structures, as shown on this project. This is P&O project, Iona cruise ship, where reducing the weight was a key in limiting the impact on the overall ship weights and buoyancy calculations. The digital design tools meant that we could reduce each of the section sizes down to the minimum, and more importantly, we could do it very quickly. But it's not just in the design that it adds value, it's also the possibility to truly link with the designers with the makers, such as 3D printing developments that make it a really interesting, exciting prospect for the future. We've recently finished our concept project using these tools, and this is for a project on Mars. In this image, you can notice that as ambitious as the architectural intents were for the glazing, the media and TV was fixed on what Motorola were producing at the time, which is perhaps understandable. This is an advert at the end of the day. But with the digital world so embedded in our culture, I see this as becoming more widespread in the future. There are technologies on the market today which integrate LEDs within the glass, but I can see higher image quality and definition and more transparency being what clients really strive for. And there are a few interesting new technologies on the horizon that will hopefully help to achieve this. As I mentioned before, sustainability is continued to be one of the key areas to develop and be in the forefront of what people are considering with the technologies. Products such as AGC's Finio vacuum glazing that avoids the need for glass valves are very promising in reducing overall U values, especially for retrofits of older single glazed panels. And retrofits, I think, will become ever more important as part of the sustainability drive. As is the latest developments in building integrated photovoltaics, we've seen the possibility for ever more transparent units through the latest generation of organic cells, which are also flexible, which allow curved elements to become a possibility. Although the efficiency needs to improve, the fact that we have so much surface area in our cities that we could utilize for energy production without disrupting natural environments whilst maintaining transparency is an exciting and perhaps necessary prospect. So just to sum up, in the same way that past authors readily offered their visions for the visions of tomorrow, I think it's important that designers and clients and contractors reflect and actively shape our future. We need to continue to engage with suppliers and specialists, and we may even discover that our wants and desires are closer to fruition, or they may even ignite an idea in a manufacturer to make them possible. This dialogue is one of the ingredients which will help our industry to innovate, and who knows, in doing so in the future, it might not be so far away. Although I hope it's not as apocalyptic as shown in this image here. Thank you.
Thanks, Ian, for that great overview and starting of today's session. Interesting the way you showed a different range of projects where different types of glass applications are possible. Now we'll move on to, I hope you can hear me.
Yeah.
Right. I don't know because, right, were you able to hear me?
I can hear you, yeah.
Okay, perfect. So thank you so much. We'll move on to the presenter, to Andreas. I'll just make him the presenter. Just a second.
So, can you see my screen now?
Yes. Can you just go to full screen mode?
Wait a second, please. To change the screens, please. 1 second. So now, can you see full screen?
Right, it's Sile now. Yeah.
Yes. Okay. So, good morning, Europe. Good afternoon, Asia. Thank you, Ian, for the wonderful talk you just had. It's a wonderful introduction also for what I'm going to show now here. Today's topic is structural glass cutting edge projects here in Southeast Asia. I want to mention in the test run, we have recognized that I have a certain time delay in changing the slides, so please bear with me if what I say is not perfectly synchronized now with the slides. But anyhow, let's see how it goes. So first, allow me a quick introduction of the company. So Seele as a group of companies, the structure. So we have Seele GmbH and Seele Austria mainly as facade contractors. And then we have here SEDAG on the right-hand top, which is a glass processor, and Sunglass on the middle right-hand side is also a glass processor, mainly for curved glasses and bended glasses. And we have a product line under Iconic Skin, which is insulated glass panels with integrated sunshades, and also GSP, a glass sandwich panel. Give me one moment, I need to arrange my screen here a bit because something is covering here my tools. Okay, here we go. So here we have a quick look into Seele's subsidiaries as a facade contractor all over the world. I am sitting here in, wait a moment, laser pointer. I'm sitting here now in Singapore. That's from where I'm talking to you guys. And what is Seele doing? The scope of work of Seele is mainly research and development, construction and planning, project management, quality management, testing, manufacturing, logistics, assembly, and installation. You would say that's typical for a facade contractor. The one thing that is not so typical is the first one, the research and development. That's not really self-understood in the industry, but here we have a very, very strong focus on. So what kind of projects are we typically doing? It's steel and glass constructions, it's membrane constructions, it's unitized facades, and all glass designs. Of course, that's what we are going to talk about today. So here's some highlights. On the left-hand top is the Chatstone in Melbourne. In the middle, we have King's Cross. On the right-hand side, we have the Tech Bridge in Toronto. Then we have an Apple store here in San Francisco with super-sized sliding doors in the middle here. Those sliding doors are 13-meter high and around 6 meters wide each. Maybe they are rather sliding gates than sliding doors. Then we have here the Strasbourg railway station, Icon Siam in Bangkok. That's something I will show later today. King Abdulaziz Center for World Culture, European Central Bank, and Canary Wharf in London with a membrane construction. So when we talk about glass as a structural element, now let's first have a look at some very basic facts. So we have different types of glass treatment. Now we have float glass, we have fully tempered glass, we have fully tempered glass heat soak tested, we have heat strengthened glasses, and we have chemical toughening, which is a technology that is, for example, used for glass stringers on spiral staircases. Of course, chemical toughening is quite limited in its sizes due to the bath you need for that. And then we have laminated safety glass, which can be a combination of any of the above mentioned glass, treated glasses. So we have to keep in mind when we look at all the projects that are following now, that the higher the strength of a glass is, the smaller are the splinters it is breaking into. And the larger the splinters are, the better is the post-breakage behavior, especially in a laminated glass package. Now we have to keep that in mind. We always have to combine these kind of glasses in the right way to achieve the structural behavior and the post-breakage behavior as we need it in our actual projects. So now let's have a look at the rooftop viewing platform and glass cylinder for the Mahanakhon in Bangkok. Here you see the project. Most of you will know it. It's the highest building in Bangkok currently with over 300 meters. There is one glass tray, an observation platform there, and there is a glass cylinder with a double cylinder with a spiral staircase leading up to the rooftop. And then you can walk over to visit here this Skytray observation deck. So it's a 60 square meter observation deck we are dealing here with. And this is what we received in the beginning, mainly with the question whether we would be interested in doing that job. So we had the first meeting, and the discussion was here that the architects and the consultants' idea was having this glass tray here with a glass member below it supporting it. So the issue was then the only offers they received were using steel members. Nobody dared to go here in such a platform with a glass member. So we went looking into that, and we came to the conclusion that it might be even better to have no glass or steel member there at all, but only have the glass panels spanning freely to the other side without any further support. So that was then the proposal we made to the client, and the client decided that that is the way to go. So when we are looking into this kind of structural glass applications, there is one very, very important factor. That is that the SGB or PVB, whatever you use for the lamination of the glass, is changing its elasticity modulus over temperature. The warmer it gets, the softer it becomes. So you have to consider that very, very carefully in the beginning of each project to come up with the right thickness of the laminated glass package. So we spend considerable time in these kinds of early assessments on a project. Then, after that is done, no, let me come back to that slide here. I want to mention one thing more. It is not only about the surrounding temperature here, it's also about the sun impact, the direct sun impact, which is heating up the glass. So this is something that is not very easy to come to a clear result, especially also because there is no code, neither in Thailand nor in Europe, which is telling you how to estimate this kind of heat in the glass. The heat is building up. There is a transmission, there is reflection, there is absorption, and the energy that is absorbed by the glass is heating up the glass, and this has to be taken into consideration in all the structural calculations you do there. So we found there is a code in Hong Kong, the Hong Kong Code of Practice for structural use of glass and steel, and this code of practice is given certain answers on that, and this enabled us then in the end to calculate a surface temperature of the glass. So of course it's very important, if you want to get the approval in the end from the local authorities in Thailand, you need to have a very, very good structural partner over there in Thailand who knows how to convince the authorities of what you are doing. Because these things were never done over there, so you have to guide the authorities and give them the certainty that you know what you are doing and that your assumptions, your basic assumptions that are leading then to your final product are based on hard facts and are realistically reflecting what you are doing there. So after we started then working on the project, obviously we had to do a lot of testing. So we did one of those classes here. We did a permanent load test. We did a hard body impact test that you can see here. And we did test the residual strength of the broken test specimen. We were, that's the test specimen here after 12 hours of residual strength test. And this was then, in the end, the result. Here you see me standing on the glass and taking a photograph below to the other skyscrapers there. And what you can see here, all these point fixings going along the facade, this is something we developed especially for that project. We call it glass retention system. We had to make sure, even if we have a total glass failure, meaning even if all those, the whole laminated glass package would break, we had to make sure that the glass can still not slip out on the left and on the right. So it can never, ever fall down with all the people standing on it. And we tested that extensively, and I can assure you this thing is as safe as any floor could ever be to stand on and to walk on. Even with a total failure, it will not fall down. It will be retained in its position. It will sag down a bit, but it will be retained in its position and be held back by those special point fixing along the edge of the glass. So here you have one more picture of the finalized project. Here's some more. So it's open for public now. I think you pay around 800 Thai bahts to go up there. You can have a great time there. There's also a bar in that area. It's really highly recommended to visit that place if you come to Bangkok. Now let's have a look at the second part here of that project. The second part was that glass staircase in the glass cylinder. And it is a double glass cylinder and a spiral staircase inside. And inside the inner glass cylinder, you have an elevator going up. So now the question was, how would we stabilize this cylinder? There is no steel construction or whatsoever stabilizing it. And it's also not fixed here to the extension of the outer facade of the building. This thing is standing completely freely. There are only two little platforms going over where the exit is of the elevator here and here. So how did we do that? We were introducing into the glass joints here tension members in the outer cylinder. So with these tension members, we are pulling down the rooftop here onto the glass cylinder, and by that compression of the glass cylinder, it is stabilized. So this is something that Ian mentioned also, not to bring tension elements into glass joints to stabilize structures. It's a little bit different than the one that Ian just showed. The idea is the same thing, tension members in glass joints. So now here you can see, for our business, it's very important that we start early with structural calculations. Our clients ask us for a pricing. Sometimes there is a tender with some estimations of glass thicknesses and glass qualities already, but we kind of always do our own estimations and come to our own conclusions before we make a price. So these here, the left one here was a very early model where we confirmed and corrected what we thought we need to correct, and we came to our own conclusion how that cylinder could work, and based on that we made a price then, and we agreed on it, and we signed the contract and executed the project. So what you also need to consider when you do structural glass, you have to control the stress on the glass along the installation. That means you need to make a structural snapshot for each phase of installation, because it is changing, stress in the glass is changing with the installation progress. So we have to model that installation progress also structurally, and to make sure that along installation there is no problem coming up there with the stress in the glass. Here you have some pictures of the installation itself. As I just mentioned to you, the outer cylinder is stabilized with a cable, and then the inner cylinder is stabilized via the roof after it is then on top of it and pressed down also onto the inner cylinder. So as long as this is not the case, we have to fix it all with the inner wooden structure here, or a wooden scaffold which we custom made for that purpose here. Here you can see another challenge in the installation was the extremely narrow space there on the rooftop. Drainage was a big issue, of course, lifting limitations and so on and so forth. So it is also logistically a real challenge to execute such a project up there in 300-meter height. Now, this is the final project here. You can see the staircase spiraling up. You can see here the stainless steel hubs connecting the glass. That's the inner glass cylinder here with the elevator coming up, and outside the outer glass cylinder. This is now the finalized project in Bangkok, Mahanakhon. Now let's have a look at the all-glass spiral staircase over 3 floors on a true digital park, also in Bangkok. This is a business park, and they wanted to connect 3 stories here with a very, very modern structure. So they approached us, and we started the discussions with them, and here you can see the final result. But what we received in the beginning was such kind of architectural design idea. So based on that design idea, we start then to develop a proposal. So we made the first 3D drawings. This is all via tender phase. We made the first 3D drawings or 3D models of it. We make the first structural calculations. Here we apply wind load. Even if it's an internal staircase, you still have to apply a certain wind load to it. Here you see the first assessment of the deformation under life load. and the people walking up and down. So after we finish all those first structural assessments, we know the glass thickness, approximate glass thicknesses, and based on that, we can then do the first visualizations. And with those visualizations, again, we convince the client, or we agree with the client on certain design. And we sign a contract and we go into executing the project. Here you see what we found on site. Since this is ground floor here, and then we had to go up for another 2 levels. So you can imagine the relative position of the inner glass cylinder to the outer edge here of the concrete needs to be perfectly aligned. So now the concrete itself is obviously not so nicely aligned. So we had to put a lot of effort into this construction here to equalize or to neutralize all the tolerances here and make the inner glass cylinder, bring the inner glass cylinder into perfect position practically here to the edge of the hole in the floor, or to the steel connection construction on the edge. This needs utmost attention, and it takes relatively long to get that properly done. Then we start with the installation. Again, here we have in a scaffold, a wood scaffold, to go up and up and up. And then when you already think you are up and you are very happy, then it happens, a glass breakage here. So, yeah, and you can see it happened on the lowest level. It's the lowest glass of all glasses. So kind of a worst case. So luckily, when we started with the design here, we had several meetings with the client, and we could agree with him that we increase the size of the stainless steel hub here, this ring that is going around the staircase. We increased it to a certain size, big enough that it would allow the exchange of a glass in case of breakage, even in the lowest level here, without de-installing the whole staircase and building it up again. That was a very, very good decision. So this glass hub here is now a little bit higher than it was originally architecturally anticipated, but it was a very wise decision to do it that way to enable us to change the glasses. So here you see the final product. This is one of those stainless steel hubs, as I just mentioned it. And I think those stainless steel hubs here integrate into the all-over architectural design just perfectly. It became a very, very beautiful staircase. I'm a big fan of it. So now let's have a look at Icon Siam. Icon Siam is a huge shopping mall in Bangkok. We finished that project a year ago now, a little bit longer. And yeah, let's look into it. We have 5,300 square meters of this luxury facade here. That's how it's called. The total height of it is up to 24 meters of spanning glasses here. The glass panes are inclined in 2 directions, and they are arranged in a jagged zigzag pattern. And the floor plan is not just a straight facade, it's also curved. So you can call it a 3-dimensional nightmare, maybe. We have 333 glasses and 333 front glasses here. So I received early 2016 with this picture the question, can you do it? So I answered back, yes, maybe. I mean, it's hard to say whether we really can do it just with that, but that answer was enough to be 2 days later in a meeting in Bangkok and discuss his project with the client. So the client had a tender out there already, but he didn't receive any satisfying answers back. Actually, he received tender queries back than answers. So the client did not want to give us the tender document, so he just gave us a SketchUp file on a memory stick. That's it. And based on that SketchUp file, we were supposed to do to come up then with a price within 2 weeks' time. So quickly, we started doing our first structural assessments again. We started doing some basic details. We did some first 3D visualizations, how the thing could look like. We went into the estimation of a project and came up with the first pricing. So here, another step, we had to look into different situations on the projects which were leading to different glass thicknesses. So that was our first estimation here, glass fin 15 millimeter red, 16 millimeter blue, and 17 millimeter here in the green area. The green area is the area where the glass fins are spanning up to 20 meters freely without any support. So that was our first estimation here, and based on that estimation, we did then our pricing. Then we did for the first pricing also, we already started to do some visualization, so the client has a better idea of what is the nature of what we are offering him here. Some more of those visualizations, and actually this kind of visualizations were later also used by the client then to show it to his potential tenants there, who were very interested in seeing the transparency of the facade, to see how well their company logos, which would be behind the glass facade, would be seen from the other side of the river, especially by nighttime. That also played a very important role here to achieve maximum transparency. So the last hurdle then to sign a contract with the client was to double check the reaction forces and on the existing structure. So this is also an exercise we had to do, reaction forces, to see whether the project itself can take the load of the glass. Originally, we wanted to stand the glass on the floor, but the project was already prepared to suspend it. So the concrete on the floor was not able to take the loads. So we had to suspend the glass then from the ceiling, which we then did. So after this reaction force check was also confirmed to be good, we could go ahead then with the project itself. So we start now the real design and engineering. We have to be clear here that the model we are working on needs to reflect the actual situation on site. Because we cannot cut any of those glasses later and adjust it to something if the concrete is suddenly a little bit in the way of the glass or something like that. So we had to harmonize all the 3D models that were out there with the architect, the main contractor, and the client and us, to have one model that really shows the final situation on site. And we had to make sure that any change that was coming from architect side is also in time incorporated into that model, to make sure that we are all working on the same data basis. Then again, this very, very important temperature issue. So also here we did an extensive assessment on surrounding temperature, on sun impact, and so on, to really know how much is the glass heating up in the built-in situation, and to from there come to the conclusion then about the glass thickness and the glass buildup. Then we did some testing here, mainly to verify also the stress around the drillings in the glass, which were necessary to connect glass fins here, for example, and under different load cases as well. After that was settled and we had the results, we went into the shop and into the fabrication drawings. Here, just in typical zone, you can imagine that with this plan drawing here, none of these situations is repeating on the building. So we have zero repetition. Every situation is different. Here you see the jagged nature of the facade. This is a glass fin here. This is a front glass. And at the same time, the glass fins are inclined, not only to this direction, also in the other direction, to the side. Then after all of that was done, we could finally go into fabrication. Here you see our steel fabrication in the Czech Republic. This is Seele Pilsen. And this here is one of the stainless steel brackets where the glass is later suspended from. So this slot here is where the fin is later going in and where it is fixed and where it is suspended from. We will see that fin later. Here you see now the glass production in Sedak. Here you see some pre-manufactured, already drilled and cut fins before the lamination process. And here you see how these fins later go into the autoclave for their lamination. Massive glasses. Then one huge advantage of to have this in-house production depth for Seele is that we can do a lot of pre-assembly already in our own facilities. No? So the steel is coming from our own steel workshop in the Czech Republic. Then it is pre-assembled in Sedak. So stainless steel shoes here are connected to the fins already, the glass fins. Here you see the final product, a stainless steel shoe with the glass fin. From here we will go into the packing. Here we build the wooden crates to send it because these things are far too big to put them into standard containers. Then the box goes onto the truck and it goes onto its way to Bangkok. Here the situation in Bangkok, the unloading in the harbor. Then we go through the narrow streets of Bangkok onto the site. Here it's already arrived on site and we are bringing our glass lifting machine, the glass suction machine here now into action. Here you see it has a head here, this head with the suction cups, and this can move three-dimensionally by remote control. And here the counterweight to keep it straight while installation. So we started installation from the right-hand side to the left-hand side. Here you see the scaffold, and on the scaffold you see these little platforms here extending out of the scaffold. Actually, these extensions here are shaping the facade already. You can see it here. It's jagged, 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 and it's perfectly pre-shaping the whole facade structure there. We need to do that because due to the fact that the fins are not vertically standing here, they would actually deflect in one direction, and we don't want that. We need to fix them somewhere, so when the fiberglass comes in between, the fins are not in their way. Here you see it now on site. You see all these jagged wood platforms fixed to the scaffold, and the glass is coming here now with the glass suction device in action. And here you see now those brackets we just saw in production in the Czech Republic, already installed now on site. And here the glass sucker in action. You see how it's turning and twisting. It needs to do all these movements so you can position the glass in all its different built-in situations here. No? So it's a real high-tech machine, this glass suction machine here. And we go along with the installation. Also, protection of glass edges is, of course, super important, while installation especially. Here you see us going along further. And now the question is, how do you check the precision of the installation? This is very important to know because you want to make sure that there is no overstress of the glass due to imprecisions in the installation. It could be enough that at one position there, the glass is 2 centimeters too far outside or whatsoever. It could already create a higher stress in the glass than what you actually want there to be. And that would be risky. So we always have to make sure that everything is installed just perfectly. So we take pictures of the facade with a special lens with a defined focal width and focal length. And with these special pictures, we overlay it then with a 3D model we have from our engineering. And here we could even see smallest deviations from theory. And we can make sure it's perfectly installed. Very important. Here we go along with the ceiling. The ceiling of this kind of constructions is very important because the ceiling is also having a structural function here. It's structural silicon. We have point fixings here, but the point fixings alone are not doing the structural job. We need the sealant, the structural sealant in addition, but it's also, of course, important for long-term water tightness, and also the sealant needs to look perfectly. So we have special sealant teams in Seele that are working all over the world for such kind of projects. Now, the sealants have to look perfectly in order to keep the wonderful architectural vision here alive, also in the smallest detail. Here we have a very proud engineer at the opening session. And at the right-hand side, you see now a view into the main entrance hall with these hugely spanning glass fins and front glasses there. So this is now, you might recall the picture I received in the beginning of the whole process. And this is the final product now, which is coming very, very close, I think, to what we saw there in the beginning. Here's some impressions of the project. Here, the point fixing, that the clamp that is connecting the fin to the front glass. Here you see now these logos behind the facade. Another logo behind the facade. And some day and night comparisons. Day and night again. And I think the visibility of those logos here is just great. It's great, even through such an odd angle here. Some more detailed impressions. And what's also great, this facade is reacting very, very strongly on the outer weather. It reflects the weather. If the weather is dramatic, the facade is dramatic. If the weather is sunny, the facade is sunny, happy. Amazing, amazing facade. So now there is supposed to run a video, but it doesn't.
Can you click on it, Andreas? It doesn't look like this video.
I'm trying here.
Is it embedded in the PowerPoint?
Something is wrong. It is embedded in the PowerPoint, yes. Something is wrong. I have no idea what it is. It was starting when I normally did the presentation. It's just now that it's not starting.
Fine, no worries. You can probably continue, and then we can go at the end. You can probably play the video.
Exactly. Let's continue now. It's a pity, but let's continue. Okay, let's have a look at the Wisdom Hall now. The Wisdom Hall is what Ian already mentioned today here. It is this triangular steel frame on top of the Iconceum with a cable facade inside. Very challenging job to do. You see here outside the Wisdom Hall, it's nothing. It's just going down with another facade. There's nothing you could work. So we are talking here about a stainless steel frame of approximately 80 tons, 64 triangular panels of glass, 14 tension cables, and 21 nodal points. So what did we do there? Since there was no area to work here on the outside, we had to build up a huge space scaffold, and we had very stringent lifting limitations there. So we could only bring up here small chunks of steel, and those small chunks of steel we had to connect here on top of that platform. And then all of that was fixed here with huge hinges against the concrete. And then it was pulled up with cables into its final positions. I have a wonderful video showing that. I'm just afraid it doesn't work now as well, the same like for the Iconceum video. This here is the final project then in the end. We also did this area here on the side. And here you are looking through the luxury facade, which I just introduced. Here a view from inside to the other side of the river. A wonderful project. And again, the video does not work. Whatever the reason might be, it shows me here running, but it doesn't run. So sorry for that. Maybe we can just have a look at it later. I will open it maybe directly from my screen. And now I have another issue here because my mouse is not working anymore. A moment. Oh, okay. All right. As a last project, let's have a look at the glass tube project for the K11 Museum in Hong Kong. Here we are using glass tubes as a structural element. Those glass tubes are spanning freely over the whole height. It is 69 glass tubes, to be more precise, inside with the so-called CCF, a closed cavity facade system. I will come to that. So this is the facade on the project, consisting of those glass tubes, 307 tubes, 919 square meters. So we have 307 tubes, as I mentioned, 238 half tubes of those and 69 full tubes. The height is up to 9 meters and the diameter is approximately 950 millimeters. The half tubes are connected here in between with aluminum profiled, and each is fitted with a polished duplex stainless steel lid on top and on bottom. This stainless steel lid here is fixed with structural silicon, and it has to hermetically seal this glass tube, because with the CCF technology, we are applying a slight overpressure of air inside the tube, and by that supplying it with clean and dry air, because we have to avoid any residue on the glass here, since these tubes are not accessible from inside. So we had to make sure that this works without maintenance from inside, and we need to be totally sure that it always remains hermetically sealed. So this is especially difficult because the building has a relatively strong movement, an interstory drift. So these lids at the top and at the bottom closing the tubes again are fixed to the construction of the building. And here you have to take the movements without ever compromising or damaging the tightness of the structurally applied lids to the glass tubes. A quite tricky design, I have to say. It looks much more like mechanical engineering than the usual facade technology. So since the structural requirements in Hong Kong are very, very high, and the local authorities, they expect a lot of structural calculations and reports and performance mock-ups. So we also had to do performance mock-ups for that and really show them that this thing in fact works. So thank you everybody for your patience. So we can try now, if you like, to run a video.
Try it and see, Andreas. We'll see if it works.
Is that okay with you? So let's try it. I will show you now the Iconsiam short movie, if it works. See it now?
Yeah.
Good.
But there's no audio, so you can give a voiceover as we discussed.
Yeah, exactly. So here you see again the design and engineering phase, modeling, the glass production in Sedak, in Germany. Highly automized production, obviously, cutting of glass, drilling of glass. The steel production in the Czech Republic, in Pilsen. Here this corner bracket we saw before. Glass after the lamination, the application of the pre-assembly of the stainless steel shoes to the glass fins. Now going into the packing, ready for shipping. Arriving in Bangkok. Going on site, unpacking. The same bracket again, our most favorite one, going into position. The Mahanakon in the background, the glass suction device. And here you see the massive glass going into position. 300-meter long. And the final product. And now the more fascinating movie, even I think, for the Wisdom Hall. This is really amazing. Let's have a quick look into that. Here on top, you see the Wisdom Hall again. Triangle glass facade with the cables inside. Here you see the pre-assembly of the steel on our huge scaffold platform. Now, welding it together, the huge hinges on the concrete, the welding process, the cables pre-installed. And now we come to the lifting. Here the basic idea was discussed, then it was visualized. And that was the idea, to get the whole frame up in one piece. And the most difficult thing, to get the final bolt on the top of the triangle then into its bracket and be sure that it fits. You can imagine that's quite a challenge, because there must not be any mistake in the angle how that things comes up. So it needs to be top precision. Here we are coming up now. We stop. And now the moment to go in. And yes, we did it. It fits perfectly. So this is how we installed that massive triangular frame here for the Wisdom Hall in Bangkok. And that is the final product then. So thank you very much. And sorry for the little problem with the video, but I hope it was okay as it was now.
Yep. So
thanks for your attention.
For that interesting presentation. We'll take some questions now. Can I request, I'll give you a break for a couple of minutes. Can I request Ian to come back on? Can we have a camera switched on? We'll take a few questions. Right, Ian, are you there?
I'm here, yeah.
Yeah, hi. So Ian, if you can just switch your camera on. So I'll take the first question for you, Ian. So the question for you is, how will you consider the glass delamination for tall glass or curved glass using laminated PVB interlayer as a fixing point?
Yeah, sure. So, I mean, we in the analysis side of things, we always allow for a degree of delamination around the fittings. So when we're modeling this in our finite element software, we do take account of that. So that's the kind of analysis side of things. And then on the other hand, testing is really important. You know, before we do any new structure that has any laminated fitting, we need to do extensive testing, or well, more importantly, the contractors like Sealy need to do extensive testing to make sure that different geometries are fully understood before they utilize on projects, because you can't always take what worked on one project onto the next one. You need to check on every individual project normally. There's normally a particular low pass or geometry configurations that need to be taken into account. Hope that answers the question.
Okay. Right. So there's another question here. Sorry if I've heard wrong, but Ian talked about integrating cables within the structural glazing to reach great heights with maximum visibility. Can you give more information on the application?
Well, I showed an example in the presentation, which is a project in Hong Kong, but it has been done on other projects as well in the past. I think at the Apple campus, and also the project which Andreas showed in San Francisco with the doors integrates a similar idea. But I mean, it's really very similar to a normal typical cable facade. It's just that we're going, okay, normally the cables are set inside or outside the glass and you see them, and we're sort of trying to utilize the fact that we normally have quite thick glass buildup. So we're thinking, why not try and push that into the plane of the glass so that we can hide it, basically, because then that takes away from the kind of you know, visibility of the cables, and you can get more of a transparent system.
Right. Okay. Andreas, I'll take this next question for you. I think this is with regards to that Mahanakon Skywalk. Are the flooring glass panels supported with point fixing on the two edges? What's the glass construction details? That is the glass thickness and how many layers?
So the point fixings at the edges there, they are not really supporting the glass. The glass is supported by a glass support. Yeah, it's just lying on something, so to say, and structurally bonded to that. But the point fixings are there to avoid that the glass is slipping out from that construction in case of break. So there's additional measure we took here to make the whole construction totally safe. The glass thickness is and the glass build-up, I can only share with you it's a multiple glass build-up and it's close to 100 millimeters thick. More details I'm not allowed to share about that.
Right. One more question for you, Andreas. Which was the CAD software used to construct the Icon CM luxury facade?
We are using different CAD softwares. There is not only one software, we use a whole bunch of it. And frankly, which one now our team was using here for the Icon CM, I do not know. I'm not aware. But mostly it's a combination of a whole package of facade softwares, of CAD softwares we are using there. And they have to work together with the structural software we are using then again. So it's a combination of different softwares.
Right. Okay. Ian, this one's for you.
Main software here for the drawings.
Okay. Ian, this one's for you. Did you consider earthquake factor? Do you consider earthquake factor as a dimension while designing for tall glasses?
Yeah, we do. I mean, most of the projects actually we work on normally have seismic requirements to meet. But you can approach it in it's just another low criteria, just as we have to deal with wind or temperatures. It's just another thing to have to consider. It does make things often a bit more complicated because we need to make sure that the connections are suitably designed, and also when we're dealing with more complex glass structures or pavilions, then the global behavior becomes even more important. I mentioned on the project in Kunming, that was a particular challenge because we had to, the whole thing's cantilevering up and we had to tie the structure down to the ground with bolts going through the glass fins. But on the flip side, the structure was below was deflecting. So we had to find this kind of sweet spot by tuning the springs within the connections to meet the seismic, but also allow enough flexibility to deal with the base support structure movement. So yeah, it's something that we always have to keep in mind, and we always consider in our designs.
Right. Another question for you, Ian. The deflection will increase if the glass length increases. What do you do to minimize the deflection of the glass?
I mean, the deflection will be what the deflection will be. So sometimes particularly for steel and glass envelopes, when we're doing grid shell structures, then we pre-cambering the structure is often developed. So we try and set the geometry higher to minimize the amount of structure that we need to put in there. So that's one way to help minimize the deflections. But I guess another aspect is to try and minimize the weight of the materials. So that kind of leads on to the digital design tools that I was talking about earlier. We have to really spend a lot of time going into a lot of detail on all the different connections, all the different elements, and not necessarily always have a default section size across the project or glass build up across the project. We maybe have to rationalize that further around the structure, and that can help to limit deflections as well.
Right. Andreas, for you, this one, who was the consultant on the K11 project, and did you have any support from any local company for the installation?
I do not know the consultant on the K11 project. I cannot answer you that, but we had our own structural engineering on board for that, and we had a local partner for that who was then again dealing with the local authorities. Yes, but since that was handled by Seele in Hong Kong, I would not know the details.
It was us.
Right. Ian,
so I'd say
yeah, I
we
think
were
you guys did it, right? Right.
Yeah.
Look at that. That makes it very easy then.
Okay, so the answer is EOC were the consultants for the job. Okay, another one. Right, hold on. I'll take last 2 minutes of question. Okay, Ian, this is for you. All the references on the Apple projects are with laminated glazing. Would this have been possible to achieve with double glazing, double insulated glazing? Was it a choice not to have thermal efficient facade in order to have a bigger glass volume?
Well, it's not true that all of them are laminated glazing. A lot of the projects we do have double glazing as well. So we can, yeah, it is possible to do with double glazing. It makes it a little bit more challenging because we have to. It normally means that we have tighter deflection limits for the glass because of the seals in the units are more sensitive to deflections. But you can still follow the same principles through, and we do it on many projects. So it's not just limited to laminated glass only, and the choice between the two historically depending on the climate and the code regulations, but more often than not now we see that as a default we need to adopt some form of energy efficient glazing.
Right. Now, a question for you, Andreas. How about drainage system for these huge glass facades? How do you manage the drainage? I think he's talking with respect to the skywalk, I think.
On the skywalk, it was a pretty easy one since the whole glass had a slight inclination there, and the water is just running to one side of the thing, and here we are guiding it down along the main facade of the building. So there is a downpipe there on one side, and that's it. That was a very simple one. It was much more complex in a situation like, for example, in the luxury facade for the Icon Siam, where you have a roof connected to a terrace connected to one side of the facade, and where you have to you have to bring away massive amounts of water in shortest time. So, but in the end, it's gutters and it's downpipes, and all of that is estimated and has to work then according to the estimation and calculations.
Right. There are a few more questions, but I think we are running out of time. I wouldn't want to take them. I'll probably email these across to you guys. So I'd like to thank Andreas and Ian for this lovely session. There are many more questions, but picking and choosing all of them is going to be difficult. So I'll end this here. So just before we end, closing comments from probably Ian or Andreas before we end this session. Any closing comments, Ian?
From my side, I think what hopefully you can see today a few different perspectives from a engineering consultant's perspective and the contractor's perspective. But I feel very passionate about the links between the design side and the consultant side and the contractor's side, and I think both have a really important role to play. And I think it's really important to get the makers and the contractors involved in projects early on to help push the boundaries really, because contractors like Seele want to innovate, they want to develop new things, but just ask them for crazy ideas and I'm sure they'll come up with it, and we will try our bit to do the same from the design side.
Right. Andreas?
Yeah, I think the possibilities we have nowadays by using structural glass are simply amazing, and we are more than happy to receive inquiries from interested clients there who want to create such kind of highlights on their buildings. So we are very into that. We can look also together with companies like Eckersley or Callahan here into such projects and to realize them, make them reality. Right.
So thank you, gentlemen. Thanks for your time. So ladies and gentlemen, that's all for for today's session. I hope you found it informative. I personally did, though I'm not a facade guy, but I got a lot of takeaways from today's talk. And one of the takeaways was you can design with unlimited possibilities with glass. You have glass almost going up to 20-21 meters. I think SEDAC does that. So of course it's not for your routine run-of-the-mill everyday projects, but it's just that we are able to break boundaries with glass engineering thanks to companies like Seale, Ekaselio Kalagan, and a lot more other organizations. So the future is bright. I think once this pandemic subsides, I'm sure things will be back to normal, and people will start challenging the glass industry more for more larger size or more complex glass facades. So thank you all for attending today's session. And next session is on Tuesday. So this one is on fire safety in facades. Don't forget to register for that at webinars.zacwf.com. Today's webinar is actually recorded, so those who have attended the webinar will get an email 2 hours from when we end today's session of today's recording, and you can view the recording accordingly. So thank you all. So all of you, stay at home, stay safe. I know there are some countries the lockdown is already over, so just to rephrase that, stay alert and stay safe. Hope to see you all guys at the next webinar. Take care. Thank you, Andreas. Thank you, Ian.
Thank you. Thank you.
Thank you,
for your time.
Thank you.
Bye-bye. I'm just closing this session. Bye-bye.
Bye.